Okay, so we covered universal gravitation. We finished up. We had calculated the speed of the moon as it orbits the Earth. Okay, that was kind of our last calculation that we did. Okay, that was this thing here. We found that it moves at just over 1 kilometer per second as it orbits the Earth. Okay, the big thing we need to remember about universal gravitation is this. Okay, that the force of gravity, or the attractive force, is between the two objects. They are mutually attracted to each other. That is the thing that is hardest to get our mind around because we see everything fall towards the Earth. Okay? When something is falling, the Earth is just as attracted to it as it is to the Earth. It is a mutual attractive force. Okay? That mutual attractive force is related to, okay, the masses of the objects, right, linearly. What were the mass to double, okay, the total mass in the system were to double, then there would be twice as much mutual attractive gravitational force, okay, and the separation distance between the centers squared. Okay, that means that the further apart the centers of the two masses become, they will be exponentially less attracted to each other. Okay, those relationships are important to understand. Okay, that ringing a bell from yesterday. Okay, at the end of the day, yesterday we actually did our first satellite motion question where we calculated the speed of the moon. Okay, we'll talk more about satellite motion later on today, but I want to have you work through a little bit of problem-solving stuff to do with just the universal gravitation. Okay, because there is something we haven't talked about yet, and that is, what if you get into a three-body problem? Okay, not the weird Netflix show. If you watch that, that's really strange. Okay, but like a true Newton three-body problem. Okay, that would mean that in a problem where there are three masses, okay, you could have this kind of a situation. Okay, so there's three masses, okay, and there would be, we'll just say like this one's 5.0 kilograms. This one is 4.0 kilograms. This one is 6.0 kilograms. Okay, these two are separated center to center by 1.5 meters, and these two are separated center to center by 1.8 meters. And then I would say, calculate the net force acting on the 4 kilogram mass. Okay? So, how many forces am I concerned with here? What's pulling on the 4 kilogram mass? Julie, what's pulling on the 4 kilogram mass?
The 5 kilogram and the 6 kilogram mass.
Right, the other two masses. Okay, the mutual attractive gravitational force, okay, between these two masses and these two masses. There's also a mutual gravitational force between these two, but we're not concerned with that because it doesn't affect the middle mass. Okay, so how many gravitational forces do I need to calculate before I can calculate their vector sum? Mark, how many? Two. Okay, I've got to calculate the force of gravity between 5 and 4, and I've got to calculate the force of gravity between 4 and 6. Okay, two universal gravitation calculations. Right? Then I've got to find their vector sum. Do they pull in opposite directions? They do. Okay, something to consider. All right, so stuff like that's going to come up. Sometimes it's as straightforward as they're in a straight line like this one, but sometimes you could get a whole bunch of masses arranged in like a box or something like that, and then it becomes, I got to calculate all of these, and then I got to draw them tail to head, okay, and do vector addition. Right? That can come into play as well. Right? Okay, so I'm going to leave you with that problem right there. Okay, I want you guys to calculate for me what the net gravitational force on the 4 kilogram mass is in this situation. Okay, give you a few minutes and then we'll walk through it together. Okay, so we already said this is going to require 2 universal gravitation calculations. Okay, so that means calculating the force of gravity between 4 and 5. So that's going to be 6.67 times 10 to the minus 11, big G, okay, times 4 times 5, those 2 masses there, divided by their separation distance, 1.8 squared. Okay, it's going to be really, really small. That's okay. All right, so 6.67 e negative 11, okay, times 4 times 5, okay, divided by 1.8?
Yeah.
Yeah, 1.8 squared. All right, so 4.117 times 10 to the minus 10. Newtons, and I'm just going to say that that's on the 4 kilogram mass that's left. It's obviously mutually attracted between the 2, but it's going to pull the 4 kilogram mass to the left. Okay? All right, and then I've got to do this one, force of gravity between 4 and 6. So that's going to be 6.67 times 10 to the minus 11 times 4 times 6, okay, divided by 1.5 squared. All right. So I'm just going to get my entry back here and change 2 numbers. Okay, so 1.5 and 6. All right, so that's quite a bit bigger, but they are quite a bit closer and there's more mass there. So it's expected that that one should be bigger. 7.11 times 10 to the minus 10. Newtons, and that's going to be to the right. Now, it's just a vector sum of all forces problem. Okay, so I'm going to take that number there and subtract the first number because they're in opposite directions. All right, so the net force is going to be 3.0 times 10 to the minus 10 newtons to the right. Okay, everybody okay with that idea? Right? It's not, this isn't complex vectors, but you will run into some where you do have to do what we did here, calculate all the magnitudes, okay, and then put them tail to head and do a little bit of vector stuff. Okay, that is going to come into play. All right, so to practice that in your workbook, if you have it printed, okay, there are some questions on universal gravitation. Okay, so I would like you right now to do questions 3 and 6. Okay, and if I can scroll up far enough with them blown up that much. Let's just do 3 and 6 for right now. Okay, and then I'll talk about the other ones that I want you to do as well. Okay. All right. So the trick with number 3 is that the masses are equal. Okay. So if I'm setting this formula up, okay, I have Fg equals big G times mass 1 times mass 1. They're the same number. Okay, what's mass 1 times mass 1? Mass 1, not 2m. That would be plus m squared. Okay, so what I really have here is big G times m squared over r squared. Okay, that's the thing. A lot of people do the 2m's, just get instinctive to do that, but it's not plus, it's multiply. Okay, so I'm trying to solve for m. Now I only have one m to solve for. It's much easier to solve for one unknown than 2. Okay, so I'm just going to bring my radius over to this side. So I'll have fg times r squared divided by big G, square rooted. That will give me m. Okay, so that would be 2.3 times 10 to the minus 8 times 10 squared divided by 6.67 times 10 to the minus 11. Okay, all square rooted, and that should give me 1.86 times 10 to the 2 kilograms. So 186 kilograms each. Okay, for that one. Okay, everybody all right with that? Okay, how many people have done number 6? Okay, I'll give you a few more minutes on number 6. I'll just put it up here. Then we're going to go back. There's a couple other ones I want to go over. All right, so two objects, each has the same mass, 200 kilograms, okay, produce a gravitational force of 3.7 times 10 to the minus 6 newtons. What's the distance between them? We're just solving for r here. So we just have Fg as big G times mass 1 times mass 1. So we also have, again, a mass squared situation here, okay, over r squared. We're just trying to solve for r, so we're going to move it to the other side, bring Fg over. So we'll have big G times m squared over Fg square rooted. Okay, so when we do that, that'll be 6.67 times 10 to the minus 11 times 200 squared, okay, divided by 3.7 times 10 to the minus 6. Okay, and when we square root that, we should get that they are 0.85 meters apart. Okay. All right, questions on those? Okay, those are pretty typical kinds of problems, as was the three-body problem that we did, okay, previously. Now, I want to give you a little bit trickier three-body problem here. Okay, I would like you guys to do questions 1 and 2 here. I'll blow it up. We'll just do question number 1 first, okay, and then we'll try question number 2, and then we'll move on to satellites. All right, so question number 1 is asking about this particular alignment of the Earth, Moon, and Sun. So during a solar eclipse, the Moon moves between the Earth and the Sun and eclipses the Sun. Okay? So I would like for you to calculate the net force acting on the Earth in that question. Okay? You will have to use some of the numbers from your formula sheet. Okay, the other useful constants, okay, mass of the Earth, mass of the Moon, mass of the Sun, okay, all of those things are there, as are the distances between them, average Earth-Sun distance, average Earth-Moon distance. Those are going to be important numbers as well. All right, so I would like for you to calculate the net gravitational force acting on the Earth in that alignment of the Earth, Moon, and Sun. All right, so this is basically the same as the three-body problem we did together a little bit earlier. Okay, we have a force of gravity between the Earth and the Sun, pulling the Earth towards the Sun, and we have a force of gravity between the Moon and the Earth, pulling the Earth towards the Sun, because they're both pulling that direction. So we got to do those two calculations. So we'll say force of gravity, SE, Sun, Earth. Okay, so that's going to be 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24, that's the mass of the Earth, times 1.99 times 10 to the 30, that's the mass of the Sun, okay, divided by 1.50 times 10 to the 11, average Earth-Sun center to center distance, squared. Okay, so punch that into my calculator and I'll have the first of 2 gravitational forces there. So 6.67 E negative 11, okay, 5.98 E 24, 1.99 E 30, and divided by 1.5 E 11 squared. All right, so we're getting 3.527 times 10 to the 22. Newtons. And that's, sorry, towards the Sun. Because we're referring to the Earth. They're actually towards each other, but from the Earth's perspective, towards the Sun. All right, then I got to calculate the other force of gravity between the Moon and the Earth. 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24, because Earth's still involved, okay, times 7.36 times 10 to the 22, mass of the Moon, okay, divided by 3.85 times 10 to the 8, the distance between the center of the Earth and the center of the Moon, squared. What's the most common mistake here? Forgetting to square the 2 radii. Yeah, absolutely number 1 mistake. All right, So 6.67, okay, E negative 11, 5.98, E 24, 7.36, E 22, divided by 8.85, E 8 squared. All right, so that's a much smaller force, okay, 1.98 times 10 to the 20. Newtons, still, from the Earth's perspective, towards the sun, also towards the moon, but it's in the same direction as the sun. Okay? What do I do with those two numbers to get the net gravitational force? Vector sum of all forces. Since they're both towards the sun, that simply means adding the two of them together. All right, so we've got a net gravitational force on the Earth of 3.55 times 10 to the 22 newtons towards the sun. You'd be surprised how many people would forget a vector on that. Okay, that does have to have a vector, as net force is a vector quantity. Okay, everybody with me on how that one works? Okay, now I want you to do question number 2. You've done the heavy lifting. You get to use these numbers again. By the way, how many significant digits should my answer have here? Where did all my numbers come from? Every one of my numbers came off my formula sheet. Do we consider all of those numbers to be absolute? There's no wrong answer for the number of significant digits here. None of your values were measured values for this question. They were all absolutes off the formula sheet. Therefore, there's no wrong answer for the number of significant figures. Okay? All right. So, now the moon's over there. You already have the numbers. You have the force of gravity between the Earth and the moon. That didn't change. You have the force of gravity between the Earth and the sun. That doesn't change. But now the net force is a little bit different because the moon's over here. Okay? When it's at its first quarter waxing, that would be getting bigger. Okay? Okay, so what changes here is we've got to put the two forces tail to head. So the first force, okay, the force of gravity between the sun and the Earth points towards the sun. Right? And we know that that one is 3.53 times 10 to the 22 newtons. Right? On the head of that, we have to put the tail of the moon's force. Okay? So that goes here. But the moon's force is tiny compared to the sun's. That's why the Earth orbits the sun and not the moon. Okay? So this one here is going to be that 1.98 times 10 to the 20 newtons, tail to head. That means our net force is that side there. Okay? Just like it would have been in the first unit. And then, of course, this will be our vector. Because the force from the moon is so incredibly small compared to that of the sun, it doesn't change the angle very much. Okay, as you can see, okay, when you did it, it was like less than 1 degree. In fact, I think it was less than 1/3 of a degree. Okay, it's not much, but it's actually enough to make the Earth wobble back and forth in its orbit. As the moon orbits the Earth, okay, and the Earth orbits the sun, the Earth's orbit around the sun, we know from yesterday, is a bit of an ellipse, but it also is kind of like this. Okay, because the moon's always pulling it one direction or another as it orbits the sun. And it's actually kind of a crazy orbital mechanics, okay, that goes on because of all the competing gravitational forces. It's actually this idea that allowed us to figure out where some of the outer planets were, okay, the ones we couldn't see with the naked eye. We watched how Jupiter and Saturn orbited, and we knew they were being pulled by other objects that were more massive beyond their orbit. Okay, so they would wobble, okay, and we would be able to detect that wobble, okay, and it would be able to tell us, okay, there's another mass, it's got to be probably about this far away, just using universal gravitation. All right, it's also part of how we detect extrasolar planets okay, around other stars, we watch the stars wobble back and forth. Okay, the stars wobble as well because of the planets that are orbiting them. Okay, and we can detect those wobbles because of the Doppler effect. Okay, the light from those stars changes its wavelength because they're moving back and forth. Okay, and so from that wobbling, we can say, oh, there must be a planet about this big, about this far away that would be pulling on that star. We can also watch their brightness if the planet's fairly big when it goes in front of the star and makes it dim. Okay, all of those things are things that we use that kind of have to do with universal gravitation. Okay, so when we do this one here, okay, what we're going to have is Pythagorean theorem, okay, of those two forces. So 3.53 with the exponents obviously on it squared, okay, plus 1.98. Okay, with all of its exponents on it squared. Okay, when we do that Pythagorean theorem, we'll get, okay, that basically it almost makes no change. Okay, 3.52 times 10 to the 22 newtons. Okay, but when we want to calculate that angle, all right, we're going to use tan. Okay, so inverse tan of 1.98 over the 3.53. Okay, and when we do that, we should get 0.3 degrees. Okay. Sort of away from the sun, okay, or to the left of the sun as it goes around. All right, everybody okay with that idea? Right. Does combine a couple of concepts from different units, maybe like what I might do on a final exam, because that would be a good way to test two concepts in one question. Okay. All right, any other questions on universal gravitation there, guys? That's about as complex as it gets. Okay, you have to do vector addition with universal gravitation. That's as tricky as it gets. Okay. All right, so universal gravitation is something that is obviously part of rocket science. Okay, NASA, the European Space Agency, okay, all the international space agencies that are present, okay, use this as part of their calculations for trajectories and orbits of their spacecraft when they're traveling from Earth to other places. Okay, this is how the gravity slingshot is calculated. Right? If we want to use the gravity assist slingshot like they did in The Martian to go back to Mars to get Mark Watney, okay, they used Earth as a gravitational slingshot. They just whipped around the Earth and went back. Okay, that has to involve many calculations of the force of gravity between the spacecraft and the planet it's using to accelerate itself. Okay? And we use that because it saves fuel. Okay? There's no way we can launch the required amount of fuel on a spacecraft for it to do all of its course corrections on its way somewhere. Right? So what we do instead is point it at a planet and go, hey, gravity's free. Okay? We'll just point it at the planet, let gravity speed it up, and then turn it real quick, because that takes a lot less fuel to turn it, and let it fly off in another direction. All right? This is how all of the spacecraft that have visited the outer planets got there. All right? From the Voyager spacecraft to the New Horizons spacecraft, it's always using a gravity assist. Okay? So if you look here, okay, obviously everything is launched from Earth. Okay? If you're looking at these lines here, these are showing all the missions launched from Earth to the other bodies in the solar system. Obviously, the moon is the most visited body. Okay, it has the most circles around it. Yeah, it's closest, so that makes sense. Don't require a gravity slingshot to get to the moon. Okay, that one we can load enough fuel on to get there. Apollo 13 did kind of use that to get back when they had their little mishap. Okay, they used a bit of a gravity slingshot around the moon in order to come back to Earth more quickly. Now, the patterns you see on there, you see how there's patterns of light colors and dark colors? Those indicate successes and failures. The darker shaded colors are failed missions. The light colored lines are successes. So early on, going to the moon was not a safe bet. Okay, you can see here, okay, there's like 3 bright lines and there's a whole bunch of failures. Okay, like it was not a high success rate trying to go to the moon early on. Okay, then we got better at it. Okay, we got a lot more bright lines and very few of the dashed lines. One of those would be Apollo 13. That's technically a failure because it didn't land when it was supposed to. Okay, going to Mars is even worse. Okay, It's like 50-50, okay, to get a successful mission to Mars. Not because it's hard to get there, okay? The challenge is we're usually trying to land. Landing is tough because you can't communicate with the spacecraft in real time. Okay? There's a communications delay because our signals can only travel at the speed of light, and that can be, several minutes to an hour one way, okay, to get there and then get back. Right? So it's not a convenient way, okay, to communicate with a spacecraft. So you basically have to go program the spacecraft and have it not screw up, which they don't do very well. Okay? Lots of them screw up and crash and become smoking craters on the Martian surface. Okay, so didn't go well. Okay, there's kind of a jinx to Mars. Okay, and most of that has to do with that. Okay, Venus, same deal. Okay, so Mars has been mostly explored by NASA. Okay, Venus has been mostly explored by, well, back in the day, the Soviet Union. Right, and they had a hard time too. Okay? Going to Venus was tricky because Venus has the opposite problem. Mars has a very thin atmosphere. It's hard to slow the spacecraft down because there's no air to break it. Okay? Venus has the opposite problem. There's way too much air and things get crushed. Okay? The atmospheric pressure on the surface of Venus is higher than the pressure due to water at the bottom of the ocean on Earth. Okay? That's how thick and heavy the Venusian atmosphere is. Right? And on top of that, it's hotter than your oven on the self-cleaning cycle on the surface. Okay? It's a real challenge to engineer something to survive those kinds of conditions. Right? So the Soviets' first few missions, you can see, were all failures. Okay? The first few got about halfway down the atmosphere before they were just crushed. Okay? Because they didn't expect the atmospheric pressure to be so great, their probes were literally crushed on the way down. Okay? They did finally succeed in getting a probe to land on the surface. Okay, it doesn't survive very long, okay, like half hour, 40 minutes tops before it just melts down. But their first successful mission was supposed to do two things: take a picture and take a sample. Okay, so it had a little like sensing arm that would just come down and touch the surface and tell them what the surface was made out of. Okay, those were the two things it was supposed to do. There's a major design flaw in their probe. Okay, the arm was right below the camera. Okay, so when the spacecraft landed, it obviously had to have a lens cap on the camera, okay, to protect the camera during descent and all of that kind of stuff. So the thing lands, there's these little pyros that explode and pop the lens cap off. Okay, you take a nice picture, and then the sensor arm goes down. What does the sensor arm sample? The lens cap. The only thing brought to Venus from Earth is the only thing that got sampled, because they put the camera right over top of the sensor arm. So when the camera's lens went off, it landed right where the sensor arm would go down. Some poor Soviet scientist ended up in a salt mine in Siberia over that design flaw. Okay? They were very unforgiving, okay? During that, but they kind of still are. So they obviously fixed that design and offset the camera and the sensor arm a few degrees for the next probe. They landed successfully several times after that. Okay? Probes were lasting almost 2 hours, okay, before they were destroyed. So, credit to Soviet engineering at the time. Okay? They corrected their mistakes. We won't talk about their methods for correcting their mistakes, but they corrected their mistakes. Okay? So lots of missions out, but once you're beyond, okay, getting to planets that are close, you do have to find a way to accelerate the spacecraft. So what we do is we launch things and we send them sometimes towards the sun. Okay, a lot of the gravity slingshots are actually around Venus. They come back, go around Earth, get a gravity slingshot from Earth, okay, and before heading out into the outer solar system. Okay, so the Voyager spacecraft, okay, that's what they did, right? And then they went around Jupiter, took lots of pictures of Jupiter, got a gravity slingshot, went to Saturn, got another gravity slingshot, went to Uranus, another gravity slingshot to Neptune. Off they went. Okay, New Horizons. Okay, it did gravity slingshots. Okay, on its way out to Pluto. It didn't reach all of the planets. Obviously, used I think just Jupiter and Saturn. I think was all it used. Okay, to get on its way out. Okay, but it is and still is the fastest man-made object. Okay, it went really, really, really fast due to all those gravity slingshots. Okay, now what's happened to those probes since? They just keep going. We can't stop them. We got them going so fast, now they're just gonna go, okay? There's not enough fuel to make them slow down and come back, plus there's no point to making them come back. So they're just on their way out, okay? Voyagers 1 and 2 are the furthest man-made objects from Earth, okay? And they are now beyond the Kuiper Belt. And they're getting out into like the Oort cloud and even into the what's called the heliopause. That is the radiation, outer radiation belts of our sun. They're essentially have left our solar system, okay, and are in interstellar space. Okay, and we do still get communications from them because, well, they don't build them like they used to, but man, those were built back when they used to. Okay, and they are lasting a very long time with their little little radiation power cells. Okay, same thing that Mark Watney dug up on Mars. Okay, the thermoelectric generator. Okay, yeah. All right, so just so you know, those gravity calculations are what allow us to get those spacecraft up to those distant spots. Okay, now we'll talk about satellites. Okay, so satellites. Okay, so satellite motion, okay, is uniform circular motion, okay, because obviously in space there's no up, down, okay. An orbit over the poles of the Earth is no different than an orbit around the equator of the Earth or any other circle around the Earth, okay. They are going to be uniform circular motion. The speed of the satellite is going to be constant, okay. The velocity obviously will be changing, okay, but the speed will be constant as it orbits, okay, whatever planet it's orbiting, okay. All right. So what keeps any satellite in orbit is gravity. Gravity acts as the centripetal force. So we were talking about that yesterday, okay? Fg provides the centripetal force for one body to orbit another, right? But it's the big Fg, okay? It's this one, big G times m1 times m2 over r squared equals mv squared over r. Okay, that is the fundamental principle behind all satellite motion. Okay, so the key to getting something to orbit the Earth is to make it go the right speed. Too slow, falls back to Earth. Too fast, it flies off. So it's a pretty delicate balancing act. Okay, get it to the right speed and then hold it there. Right? That speed is dependent on where you want to park that satellite. If you want it in low Earth orbit, where the International Space Station is, if you do, it's got to go pretty fast. Okay? The closer you are, the faster you have to go. Okay? If you're in geosynchronous orbit, you don't have to go nearly as fast because you're much, much further away. Okay? So the big challenge in early satellite motion, okay, was to get the spacecraft going fast enough that it would stay in orbit. Right? What was the first thing to orbit the Earth? The moon. Come on, the moon's been around for a long time. What was the second thing to orbit the Earth? Sputnik. Yeah. Okay, Sputnik. There's the little Russian satellite. Okay, it was just a little ball with like 4 antennas coming off the back of it. Okay, looked like a basketball with 4 tails. Okay. The Soviets launched it, and it scared the entire world because it went around the Earth and went beep, beep, beep. Okay. Yeah, well, people were more easily frightened there. Because they figured if they can put a satellite in orbit, they can put a nuclear weapon in orbit. They're absolutely right. Okay? That was kind of the idea behind intercontinental ballistic missiles. Okay? If you want to have a missile travel from one part of the Earth, like from Russia, let's say, to North America, it has to basically go into low Earth orbit and then fall. Okay? That's basically how they work. So once you could get something to orbit the Earth, that meant you could attack any point on Earth. Okay? That was scary at the time. Right? But it was also a huge technological advancement. Now, Sputnik didn't stay in orbit for very long. The challenge was you had to make a very, 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 very powerful rocket to even get a small mass to stay in orbit around the Earth, because it had to go really fast. Okay? And that's why the early space program was plagued with things that blew up. Because the way to make a rocket more powerful was to make it bigger and have more fuel, and that usually led to things blowing up spectacularly. Okay? Once we got that figured out, then we got better at it, okay? And we were able to make things orbit the Earth more easily. Okay? All right, so we're going to talk about kind of what things can affect a satellite's orbit, orbital speed, orbital period, okay? So how long it takes to go around the Earth, all of that kind of stuff. Oh, that forgot to put the square on that. Okay. So the idea of getting something to orbit the Earth has been around since Newton's time. Okay? Newton, near the end of his career, it was kind of so far beyond what was physically possible in terms of experimentation that he was down to running thought experiments. Okay? He would just come up with things in his mind and run the experiment in his imagination and then tell everyone how it went. Okay? And he was so widely respected that that was okay. All right? So this was one of his thought experiments, how you could get an object to orbit the Earth. Okay? So what you do is you take a big cannon up to the top of a really tall mountain, and as long as you can fire that cannon fast enough, the cannonball would orbit the Earth. The trick is that the Earth has to be round. Okay? That was part of it. Okay? And that the object had to go fast enough that the distance it falls is equal to the distance the round Earth curves away from it. That way it never gets any closer to the center of the Earth. If it never gets any closer to the center of the Earth, then R stays the same and it orbits the Earth. Okay? Within the Earth's atmosphere, that's impossible. Okay? Because, well, that's what causes meteors and satellites to burn up when they re-enter the atmosphere. Going really fast through the Earth's atmosphere causes a lot of friction. Okay? So this experiment would never work because whatever you fired at 8 kilometers per second would simply burn up. Okay? So what has to happen near the Earth's surface is, in order for the Earth to curve away 4.905 meters, which is how far an object falls in its first second of falling, you have to go 8 kilometers. Okay? Over an 8 kilometer distance, the Earth will curve away 4.905 meters on average. Okay? That's pretty fast. Right? Low Earth orbit, it's not nearly that fast. Okay? It's like half that fast. But you still have to go very, very fast in order to make something orbit the Earth. Okay? Everybody all right with that idea? So Newton had that idea hundreds of years ago. The technologies just had to catch up. Okay? The ability to make something go that fast. Okay? All right. So the idea goes as follows. If you get it going not fast enough, it falls to the Earth. Okay? Not fast enough, falls to the Earth. Not fast enough, falls in. It's just a projectile arc. Okay? Satellites are just a projectile. But their projectile arc never re-encounters the Earth. So it becomes a circle, an orbit. Okay? So when you fire a satellite into orbit, it's always falling. That's why on the International Space Station, you are apparently weightless. Okay? If you're falling here on Earth, you are also apparently weightless. You don't feel your weight until the normal force can push back. So any object that's always falling, a satellite, would feel apparently weightless. So on the International Space Station, your worst nightmare comes true. You're always falling. But the sudden stop never happens. Okay? You just go around the Earth and always fall. Okay? But you're going fast enough that you never get any closer to the Earth. All right. Now, a little bit of math here that we got to talk about. Okay? Sometimes a question will involve orbital period. So big T. How long does it take the object to orbit the Earth? Okay? So normally we would set up satellite motion like this. Okay? Obviously, period isn't part of that. It's not in that formula. However, certain types of questions may give you the period and then ask you to calculate the orbital radius. Okay? Problem with that is, if I don't know what the radius is, and I don't know what the speed is, it's pretty hard for me to do this calculation. So here's what we have to do. Okay? It's called substitution. You've done it before. Right? Do I have another formula that we've used in this unit that has V and big T and R in it? What is it, Caleb? You're nodding your head yes.
V equals 2 pi r over 3.
Right. V equals 2 pi r over t. Now, if you were given r, okay, and you had all the other numbers and they just wanted to know the period, you could just calculate v and then do a second step with this formula and calculate t. No problem. Okay? The problem arises when you don't get v and you don't get r, but you get t. Okay? Now there's no way to use this formula either, because you have two pieces of it that you don't have. Okay? So here's what we would do. We would plug in that formula for v. That's substitution. Okay? So rather than just saying v, I would put this formula in for v. Right? But in that formula, v is squared. So what do I have to do to that formula? Squared. Okay, so what's 2 squared? 4. Okay, what's pi squared? Is a trick. Pi squared. Okay, what's r squared? R squared. Okay, and t squared. Okay, so that's that formula squared. So here's what I do. Okay, I just put it in there. Okay, now I've substituted that formula in for v. Do I have to do a little bit of canceling? Okay, I do, right? Because I've got a r squared on the top and an r on the bottom, so what's going to happen to the r on the bottom? It's got to go away, right? Whoop. Okay, and that's going to cancel, and then I'm good. Okay, now I could start manipulating and solving for something else. Okay, it's not a like tricky math thing. You've done it in math tons of times, but we've never had to do it in this course. Okay, where we substitute a formula in for a variable. Okay, but it's going to come up. Situations like that are going to come up where you have to do that. Okay, so there's lots of different kinds of orbits, but satellite motion applies to all of them. It's just the trajectory you launch the satellite at. Okay, orbiting over the poles is no different than orbiting over the equator. Okay, the principles are still the same. Okay, if you have an elliptical orbit, then obviously your speed's going to have to change because you're going to get closer to the Earth and then further away. It's still possible to set that up. Okay, you can make satellites do that. Lots of the satellites we have orbiting like Jupiter and Saturn actually do have highly elliptical orbits because we want them to see different things, so we don't just want them orbiting in a circle. Okay, still possible to set those up. We're going to focus simply on circular orbits. Okay, now the distance orbits. Okay, low Earth orbit means you're pretty close to the Earth, okay? And you're orbiting the Earth a lot. Okay, you're circling the Earth with a low period. Okay, for example, the International Space Station, they have 18 sunrises and 18 sunsets a day. Okay, because the orbital period of the International Space Station is like 90-some minutes. Okay, so they go around the Earth every hour and a half or so. Okay, that makes some sense? That's because they're in low Earth orbit. What's the orbital period of a geosynchronous satellite? Maybe I better ask, what's a geosynchronous satellite?
Is it a satellite that goes around at the same speed that Earth rotates?
Right, it goes around at the same speed the Earth rotates. In other words, it stays over the same point on Earth. Our communication satellites, our GPS satellites are all in geosynchronous orbit, okay? Because they work way better to do their job out that far, because then they're always over the same spot, okay? When satellite television first came into being in like the late 70s, early 80s, it sucked, okay? It was terrible. First off, you had to have a giant dish in your backyard. Okay, not like the little thing that you have on your house if you have satellite TV now. Okay, you had to have a satellite dish that was probably 8-9 feet in diameter. Okay, so it was big. All right, and it was motorized. So what it would do is it would find a satellite and then it would follow it, and it would keep the signal. So it was constantly moving, following a satellite, and then that satellite would go over the horizon. So now what does the satellite dish have to do? It's going to go back to the other horizon to find the next one coming in line. Do you know when that always happened? Double overtime, game 7. Okay? Someone's just wound up for the one-timer that's going to win the Stanley Cup. And the satellite goes over the horizon. Now, it's like a minute and a half while your satellite dish goes back over, reacquires the next satellite in line, and then there you're watching them drink out of the Stanley Cup and you missed the whole thing. Okay? So early satellite TV was free. All you do is buy the satellite. Okay? There was no like coding or anything like there is now. Okay? But there was a limitation to it. Okay? And that was it. Now, we just put the satellites in geosynchronous orbit because we have better technology for doing so, and you can have a satellite dish that just sits and just points generally south, and it gets satellite signals. Yeah. Okay, so it works a lot better, okay, because we're using geosynchronous satellites rather than ones that are constantly going around and around. Okay, so that means if it's going to stay over the same point on Earth all the time, it's got to have an orbital period of 24 hours. If it's going to stay over the same spot on Earth, it's got to take the same amount of time to go around the Earth as the Earth takes to spin around one time. Okay? So those obviously have to be a lot higher up. Okay, so geosynchronous orbits, low Earth orbits, okay, that's kind of what we're going to focus on. Okay, so if we want to find, this is what we just did here, the substitution. If we want to find the period of the Earth's or of the satellite's orbit, then we just do that substitution. Okay. Okay. So the one thing to note here is what actually affects the orbital period and orbital speed of the satellite. So if we set up this formula. Okay. Yesterday, when we did the speed of the moon, one of these masses canceled. Okay. Which mass was on both sides? Mass of the Earth or mass of the moon? Okay, because if we're looking at this, mass of the Earth, mass of the moon, that mass is either the mass of the Earth or the mass of the moon. Which one is it? The one that's on both sides is the mass of the moon, because it's the one that's actually doing the circle, right? The Earth is at the center, so it's not doing the circle. Okay, the moon is what's doing the circle. So here's what that means. The mass of a satellite has zero effect on its speed or period. Okay, so the moon where it's at, we could have the moon there, 7.36 times 10 to the 22 kilograms, or we could have Sputnik out there, okay, whose mass was like 200 kilograms, okay? It wouldn't matter. They would both have to move at the same speed to stay in orbit at that distance. Their mass is irrelevant, okay? So figuring out how fast the satellite has to go does not actually involve the mass of the satellite itself, okay? Because that is going to cancel because it is on both sides. Okay, so if you're ever doing a satellite question and they don't tell you the mass of the satellite, that's okay. You actually don't need it. All right. All right, that's the one we did yesterday. We calculated the speed of the moon as it orbits the Earth. Okay. Let's have you try those two. Okay, they're satellite questions. Neptune is the satellite of the sun. Okay, so set them up and see if you can calculate what's being asked for. They both start out FC equals FG. Okay, let's have a look at the first one here. All right, so we know Neptune's average orbital radius, okay, it's 4.50 times 10 to the 12 meters from the sun, about 30 times further than Earth, okay? And we know the mass of the sun. We don't need to know the mass of Neptune because it's the satellite, and the satellite's mass would cancel, okay? So what we're gonna have here is big G times the mass of the sun times the mass of Neptune over the radius of Neptune's orbit squared, okay, equals m of Neptune, okay, times the speed of Neptune squared divided by obviously the radius of Neptune's orbit squared. Or sorry, not squared, just the radius of Neptune's orbit. Okay, so I've got to solve for v. So I'm going to bring the radius of Neptune's orbit over here, okay, by multiplying both sides by it. And that's going to cancel off the squared on the bottom. I'm going to divide both sides by the mass of Neptune, so it's going to cancel. And then I'm simply going to take the square root. So what I'll be left with is 6.67 times 10 to the minus 11 times 1.99 times 10 to the 30, mass of the sun, divided by 4.50 times 10 to the 12 meters. Okay, so Neptune is moving at 5,000 or 5.43 times 10 to the 3 meters per second. Okay, pretty quick. It's got a lot of distance to cover though because it's so far away. Okay, everybody with me there? All right. So for number 2, okay, you've got the moon Miranda orbiting Uranus. Okay, they give us the speed, and they simply want us to calculate r. It's just a different manipulation of the same formula. Okay, we would simply have big G times the mass of Uranus times the mass of Miranda over r squared equals mv squared over r. Okay, mass of Miranda is going to cancel. We're looking for r, so we're going to bring r squared over to this side. Okay, so that's going to cancel this r, going to cancel the squared. Okay, and then we will bring v squared to the bottom. Okay, and then we'll be solving for r. Okay, we'll get 1.30 times 10 to the 8 meters for that. Okay, solving for that. Okay, so satellites, natural satellites in our solar system. Okay, when you have a planet that has only one moon, it's easy to know what to call it, a moon. But if you are a planet that has more than one moon, it becomes a little trickier. Believe it or not, there is actually a set of rules in place for naming the moons around any given planet in our solar system. Okay, for Mars, what are the 2 moons of Mars? There's some useless trivia for you. Okay. Phobos and Deimos are the moons of Mars. They are the companions of war. Mars is the god of war. Phobos is fear. Deimos is panic. They are the 2 things that go with war. Any other moon ever discovered around Mars, not that there will be, but if there were, okay, would have to have a war theme to it. Okay? Around Jupiter, this one will get you. Jupiter has like 80 moons. Every moon around Jupiter is named for a lover of Zeus. Yeah. A little morally bankrupt, maybe, Zeus. Okay. Yeah. And not all of those lovers were necessarily willing. He was not a good guy. Okay. Around Saturn, they all have to do with the Titans. They're all named after the Titans. Okay. And Saturn actually has the most moons. It's like over 100. Okay. It's ridiculous. For Uranus, they're all Shakespearean characters. Okay. Miranda's from A Midsummer Night's Dream. Okay, so all of that, there's like Puck and all of those, they're all Shakespearean characters. And around Neptune, they all have to have an aquatic theme because Neptune's obviously the god of the sea. Okay, around Pluto, they all have to do with the underworld. Okay, Charon, the biggest moon of Pluto, is the name of the boatman who takes you across the river Styx. Okay, and then all the other ones have to do with the underworld. So if you ever discover a moon around another planet, you don't just get to name it whatever you want. There are rules. Okay? Now there is some useless trivia. Okay? You can take that away with you. All right. So tomorrow, guys, we will be working on satellite motion and probably move on to gravitational field strength. I will post the unit exam review sometime this week. Okay, and we'll do a unit exam review probably on Monday.